Good morning, everyone. There's a few people still trickling in. Everyone having a good conference so far? Excellent. Before I start, I just want to say it's an absolute pleasure to be in this beautiful city of yours and speaking for the first time at NDC Porto. And anyone who's watching the video, you should definitely come along to NDC Porto next year. So hopefully this is the title of the talk you were expecting. Sorry I'm a little bit out of breath. I left it a little bit late, so I've rushed here. So hopefully I'm not panting down the microphone too much. So very briefly, my clicker works. My name's Shahid Iqbal. I'm a freelance hands-on consultant working in .NET, Azure, and more recently kind of Kubernetes-related projects. I'm a .NET developer. I've been for about 10 years. And I'm also a Microsoft MVP. I'm based in the UK. I tend to work anywhere. And I also co-organize a meetup in the UK. So in Milton Keynes. So if you're ever in the UK, hit me up. We'll see if we can get you along. It's also a good opportunity just to say to people, if you're sitting in the audience and you're thinking, hey, I could do this, especially after this talk, you probably think, hey, I could do this. I definitely encourage you to get started. So get in touch with the meetup, do lightning talks, just get into it. As soon as you start doing it, I think you'll love it and you'll get a bit of a bug. My DM's always open on Twitter, so feel free to get in touch. In fact, main reason for this slide really is my contact details. We'll see how we do for time today in terms of Q&A. But if we don't get a chance to do Q&A after this session, I'll be around till about mid-afternoon before I have to leave. If not, get in touch with me on any of those contact details there. I'm probably most active on Twitter. But as I said, DMs are open on Twitter, and feel free to DM me on LinkedIn as well if you prefer. So in terms of what we're going to cover today, we're going to go a bit more detailed into Kubernetes, particularly around scheduling. We'll talk about mission controllers, so how we can take a bit more control over what Kubernetes does. And then we'll talk a little bit more around extending Kubernetes even further. And then we're going to switch gears a little bit, talk about autoscaling, in particular this kind of virtual node concept. I'll finish off, I'll touch on service meshes. I'm not going to go into a huge amount of detail on service meshes. There's another session immediately after this in room 4 with Ben Hall, who'll dive a lot more deeper into service meshes. So what I'm not going to cover, fundamentals of Kubernetes. So assumption is everyone here has a fairly good grasp of Kubernetes fundamentals. I'm not going to deep dive into how we create custom controllers and operators. Now, if you don't know what they are, that's fine. We'll cover them in a little bit. And finally, we won't deep dive into service meshes. Again, there's another session that'll do that. So now it's time for you folks to do a bit of work. So stick your hands up if you're working with Kubernetes on a regular basis. Yeah, kind of as I expected, most of you. In production? OK, a lot fewer hands. Cool. And anyone here who doesn't really know anything about Kubernetes, don't be shy. It's just useful to know. I can hopefully tweak some of my content. Good, OK, excellent. So I want to talk about pod scheduling. When we look at the control plane in Kubernetes, there are a number of components. But the interesting one is scheduler. I used to do a talk, it was an introductory talk, and at this point I would mention the scheduler, and I'd say, scheduler's job is to figure out where to run your containers. And then I'd have to move on. And there's so much subtlety and detail within the scheduler that I want to cover today. So we look at what the scheduler does. It's actually quite simple at a high level. You create a deployment or a pod. The scheduler essentially determines there's no node assigned to that pod, and will assign a node to it. It's really that simple. The key thing to understand is the scheduler's job isn't to run your pod. It's just to essentially assign it to a node. At that point, other things kick in and start running your actual workloads. So what if we want to have some control over where we put pods? So by default, we can schedule containers, pods within Kubernetes, and Kubernetes will figure out where to run them. And for most people, that's probably fine. But sometimes we need a little bit more control. So what if we have heterogeneous clusters? The clusters have got some specialized software, hardware in them, and we want to be able to utilize those effectively. We may have multi-tenancy teams. We may have a cluster that's multi-tenanted, and we want to allocate resources to certain teams. Maybe we've got some regulatory requirements. We've got some specialized hardware, and we've got some workloads that must be run on those hardware for regulatory reasons. So we might want to influence the scheduling in that situation. Or from an application architecture point of view, we may want to essentially ensure that certain components are located together or apart from each other based on our specific requirements. So this is why we might want to influence the scheduling. So there's a number of ways we can do this, and we'll dive into them in a second. So we've got node selector, we've got this node affinity, anti-affinity, we've got this concept of node taints and tolerations. We can have pod affinity and anti-affinity, and finally the kind of nuclear option, a custom scheduler. So node selector. Node selector is the default, the most fundamental concept within Kubernetes for influencing the scheduling. Essentially what we do is we add a key value pair label to our node. So in this case, actually incidentally, the K on my machine is always alias to kubectl, so I'm just lazy. So every time you see K, that's kubectl, kube control. So I do kube control label node, I give it the node name, and then I give it the key value pair. So in this case, team equals foo. What I can then do is in my pod spec, I can specify a node selector element, and then I give it that key value pair. So what Kubernetes will do is when it goes to schedule this particular pod, it will look for a node that matches that label. If it finds it, it will use it. If it doesn't find it, it won't schedule that pod. So it's very all or nothing. Nodes have a lot of labels applied to them. Some, more often than not, most of these are applied by your cloud provider. So this is an AKS node, and we can see there's a few AKS-related nodes labels on here. So we can see the machine type up here. We can see the node pool and the regions and things like that. We can obviously add our own as well. So the problem with node selectors is they're very binary. It either works or it doesn't. And we can only match on essentially an equals. So node affinity allows us to attract based on labels, but it gives us a bit more flexibility. So what we can do now is we can now match on conditions. So we can say if a label exists, if it doesn't exist, if it's in a range of labels, if it's not in a range of labels, if it's greater than, if it's less than. The nice thing is we can also be selective about how demanding we are. So whereas the node selector essentially said it runs or it doesn't run based on the presence of the label, we can be a bit more specific now. So what we can say is, if we supply the required during scheduling, ignored during execution attribute, that's a bit of a mouthful, what we're basically saying is this is a hard requirement. If this label doesn't exist, don't run this pod. Alternatively, what we can do is we can do preferred during scheduling, ignored during execution. Now, this is our soft requirement. So if a node doesn't exist that matches that label, it will still schedule it somewhere else. Now, if you're looking at this and you're thinking, well, that's a lot to say when the only thing that's changed is required and preferred, what's all of this? Well, there's actually a third option, which says required during scheduling, required during execution. Now, this actually isn't implemented yet. So what the difference is preferred during scheduling, as the name suggests, is when you are scheduling pods, it will check that label. During execution, will potentially run if you add a label to a node when there's existing pods already running. As I said, this is not implemented. There's another way of effectively doing this. So let's take a look at the YAML file for this. So this is a node affinity. So in the pod spec now, I have an affinity. Node affinity, then I've got that really long attribute. Then I've got my selector. So in this case, I'm saying the instance type is in, and I'm using an in, but I've obviously only got one value at the moment. I could supply multiple values in there. So that was the hard requirement. So the soft one has got a couple of extra bits in it. So now we're saying preferred. And because we're saying preferred, we need to essentially give Kubernetes potentially a range of options. And we apply this weighting to those range. So we're saying match in this. Obviously, if it doesn't find it, it will still schedule it. But the weighting is applied if there's multiple matching nodes. It tries to use the weight to figure out exactly which one to use. So that was kind of node affinity, anti-affinity. There's another concept called taints and tolerations, which initially sounds quite similar. So this allows nodes to repel pods based on a taint. So what happens is you taint a node, and then the pods potentially tolerate that taint. The way taints are specified, they have three parameters. They have a key, a value, same as the labels. They have this additional label, which is called effect. And we have the option of saying no schedule, prefer no schedule. So again, hopefully you can see the difference there. And then no execute. It's worth noting that Kubernetes actually adds taints to nodes under certain conditions. So if your node is running out of disk space, for example, Kubernetes will actually taint the node automatically and try and minimize things being deployed onto that node. Same for memory and various other things. So the key thing here is, if you've got a node with pods already running on it and you apply a taint, then those pods potentially will get kicked off that node. So this is the key difference between the node affinity and the taints. So we will look at how we taint a node. We do kubectl taint, we give it the node, and then we get that key value, and then colon the effect. So in this case, no schedule. So if I take a look at deployment, so I've got 3 replicas deployed onto a 3-node cluster with nothing applied other than that taint. Typically what we would see is we would see 1 deployment per node. In this case, what we're seeing is, because we've got that taint, node 0 isn't being used. So we've got 2 deployments on node 2, and then 1 is on 1. Now, if we come into our pod spec, we apply a toleration. So we say key name equals that, no schedule. What that will do is that's telling Kubernetes that this particular deployment can tolerate that taint and will allow it to be scheduled. If you're looking at this commented line here, tolerate seconds, I think this is a little bit confusing. So if you don't specify this, then essentially the Kubernetes behaves the way you'd expect. If you apply that toleration seconds and you give it a value, when a taint is applied to a node, Kubernetes will wait that long before it kicks that node, that pod off that node. So even though it's got toleration, by specifying that toleration seconds, you're giving a lifetime to that toleration. I think that's a little bit confusing personally, but that's the way it works. So once we apply that toleration, if we run that deployment again, we can now see we're scheduled across the nodes as expected. So now if you're looking at this and you're probably thinking, what's the difference? I wouldn't blame you if you're a little bit confused at this point. So let's try and hopefully clarify it. So with node affinity, what you're doing is you're telling a pod to go to a particular node, but the pod is explicitly has to essentially say not to run on a particular node. So the node doesn't have any control over what necessarily runs on it. Anything can be scheduled. Difference with a taint is basically saying don't put anything on me, don't allow anything to schedule unless they explicitly say so. So what you can do is with the taint, you can prevent kind of casual scheduling. So if you've got a resource, a node in there which has got some expensive resources on there, you don't want it to utilize it all the time, you would use a taint to prevent that being deployed. Because essentially nothing will get deployed unless it explicitly says it wants to be. We'll take a look at this in an example with the scaling later on. So we've talked so far about kind of pods to nodes. Another scenario we may want is to be able to control where our pod goes based on what else is running on a particular node. So this is where kind of inter-pod affinity, typically just called pod affinity, pod anti-affinity. So this allows nodes to be selected based on what other pods are running on that node. So this allows you to ensure that maybe certain components run together on the same node. So maybe you've got a cache alongside an app. Alternatively, you may want to separate certain components. So for example, you maybe want to ensure that your replicas don't run within the same availability zone. You can separate them out using pod anti-affinity. And then this way, if there's a loss of a zone, you don't get even a temporary drop in your availability. Let's take a look at an example of how this works. So you've got, similar to the node affinity, you've got the constructs of kind of indicating how strict you want to be. So you can do required and preferred. You've got this additional concept of a topology key. This is initially a little bit confusing, but hopefully we'll clarify as we go along. So this references a node label, and essentially says Kubernetes, what level, in quotes, what level of my infrastructure am I using to apply this separation? So this can be a host name or a failure domain. So hopefully clarify a little bit now. So I've got a kind of 4-node cluster here, and if I apply a label of a host name, got host name node 1, node 2, node 3, node 4. The topology key will treat these as 4 separate zones, if you like, 4 separate clusters, 4 separate nodes, as you'd expect. Alternatively, we may want to separate by zone. So now we've got the first 2 machines are in zone 1, the other 2 machines are in zone 2. If we use the topology key of zone, Kubernetes will actually treat these as 2 potential locations, and it will schedule on any one of those 2, unless you've added additional selectors as well. So let's take a look at the YAML. So now, again, within our affinity section, we've now got a pod affinity, got required doing scheduling, blah, blah, blah. Got the label selector, so now I'm saying match on my component in values cache. Now, these are the labels on my deployment now. Yeah, so these aren't labels on my nodes, these are labels in my deployment. And then finally, I've got my topology key, which is a label on my node. Let's try and visualize this. Hopefully, this makes it a little bit clearer if you're still confused. So I've got 3-node cluster. I've got this web component. I've got a cache component. I want to deploy it. I want to spread them across the 3 nodes. And I want to always ensure there's a cache and a web component next to each other. Now, that may happen if I just deploy this. I want to ensure that happens. So what I do is for my web component, I set a pod affinity with the cache component, and I say that's preferred. The reason it's preferred is because the cache may not be deployed, and I don't want it to be a hard requirement. I set an anti-affinity to itself. So I want it to do is repel itself so that it goes across the nodes. And then the topology key I want to be the host name, because in this case, I want to spread it across the 3 hosts. So if I deploy that first component, I get those 3 components, as we expect. Now with the cache, very similar. This time, I'm saying pod affinity to the web component, so I want to attract it to the web component, and I want to repel it from itself. And again, I'm using the hostname topology. And of course, that'll do as we expect. If we take a look at the YAML for this, it gets a little bit longer. So now we've got that pod anti-affinity. I'm saying it's required, and it's anti-affinity to itself. So this is the web. This is the web front-end spec. And then I'm preferred affinity to the cache, the component cache, and the host name topology key. Same with the cache. I won't necessarily label the point. Required anti-affinity against itself, affinity to the web component. And then if I deploy this and I get pods, what we can see is, if I order by the nodes, we can see node 0 has got cache in the web, node 1's got cache in the web, node 2's got cache in the web. So we quite quickly went through a number of different options there for scheduling pods. What if all of these different constructs still don't give you enough power? The other option, the nuclear option as I like to call it, is you can write your own custom scheduler. You can write a schedule in any language you want. I've seen examples in Bash, for example. Don't ever use that in real, but there's examples on GitHub if you want to have a look. It needs to have access to the API server, because that scheduler needs to be able to get all the pods that have no node. It needs to be able to assign nodes. It needs to save that back to the API server. Once you've got that custom scheduler running, all you do is you specify the scheduler name section, and you give it the name of that deployment. So actually, it's quite easy to use once you've created the scheduler. So as you can hopefully see, there's quite a lot of options on tweaking how Kubernetes schedules your pods. As I said at the start, it's worth remembering, you might not need to do any of this. Kubernetes is very powerful. You can usually just let it do its thing and only dive into these things as and when you need them. What if that's still not enough? What if you need to take a bit more control? Let's say you want to have control over what resources are created within your cluster. You might want to apply custom policies. You might say that every deployment must have a certain label applied. You might want to prevent certain resources from being created. Or you might just want to inject some additional logic transparently into the resources. So if you're a cluster operator, you may want to apply some policies that run, and your developers don't necessarily need to worry about the policies. Policies just get injected in transparently. So they don't need to remember to reference them. They just get applied automatically. So this is where you can potentially use admission controllers. So admission controllers are essentially code that intercepts API requests after they're authenticated, but before they're persisted in the etcd cluster. These controllers, they can be validating controllers. Essentially, they can just inspect the resources being created and validate them, but they can't modify them. You have mutating, which can modify them. And then admission controllers can be both. They can validate and mutate. These admission controllers are enabled or disabled within the Kube API server. Now, if you run Kubernetes on the cloud, if you run a managed Kubernetes provider, how many people are running Kubernetes entirely by themselves? The full cluster, fully managed by themselves. So 1 or 2 or 3 people. So most people are going to be running in the cloud, whether it's AKS, whether it's GKE, whether it's EKS. The problem is, within those managed providers, you don't have any control over these particular flags. They're set by the provider. They're also compiled into the Kube API server binary, so there's not a huge amount of options there. You can't really create any yourself. There's a number of these built in. I'm not going to talk through all of them, but you can check with your individual cloud provider which ones of these are enabled or disabled. If we take a look at the lifecycle of an API request, we'll see where these fit in. So we make an API request to the HTTP handler, receives that request. It will authorize it, authenticate and authorize it. It then runs a mutation admission controllers. So these are things that may be changing the resources, maybe creating brand new resources. After that, we run this object schema validation. So it makes sense, we validate after we've done the mutations. That makes sense. Then we run the validation admission controllers. They always have to come after the mutations, as I'm sure you can imagine. Otherwise, you can bypass validation by mutating. And then those things are persisted in etcd, and then whatever other control loop kicks in to start doing the actions. Within these mutating and validating admission controllers, there's 2 specific ones. Mutating admission webhooks and validating admission webhooks. Everything's a bit of a mouthful, isn't it? These 2 are really interesting because they allow us to extend Kubernetes without having to write new API server binaries, without having to change the startup flags in API servers. So if we're running in the cloud, these are really powerful. So these 2 special admission controllers, which, as far as I know, all the main cloud providers have enabled, essentially allows us to create a webhook. So when we create new resources or we modify existing resources, we can write a mutating webhook, or we can write a validating webhook. And all they do is they essentially invoke a HTTP callback. So basically standard webhooks. The nice thing with this is the logic for these callbacks doesn't need to be compiled into the API server, so you can write it yourself. And in fact, the logic doesn't even need to be within your cluster. So let's have a quick look at a demo. And I'll bring it up on the screen in a second. Cool. Can everyone see that at the back? Can we see that at the back? Yep, cool. So what I've got here is I've got a validating webhook configuration. So I'm basically specifying one of these webhooks. The bit at the top is not that interesting. We have to give it a unique name, and then we specify which rules this particular validation applies for. So in this case, I've said it's on all API groups v1 for the create operation of pods. This failure policy essentially says, what should I do if the webhook itself fails for a technical reason? If there's no connection or there's a drop in the network. So fail will basically say this treats it as if it's failed validation. And then I've got the actual config itself. So what I'm actually going to invoke. So in this case, I'm going to invoke an Azure function as the validating webhook. I'll show you the demo. Before that, let's have a quick look at the code for that webhook. So I've taken an example that Kelsey Hightower did and I've adapted it for Azure Functions. So the top bit hopefully is reasonably familiar for people who use Azure Functions. We get the request in. We just need to kind of loop through the spec, look at the containers. In this example, what I'm going to do is I'm going to check if the container matches a particular container name. So the kind of contrived example here is I've got a particular image that I don't want people to run. So I'm going to use this webhook to basically prevent that. So if that webhook matches this particular image, v1, then I'm going to return this response, which is a failure. And I'm going to say, it's using a bad image, we're not allowed. Otherwise, we just return essentially allowed equals true. So hopefully, reasonably straightforward. So if I come over to, well, don't look at my desktop. Come to Azure Functions, and what I'll do is let's just refresh this. Oh, yeah. Interesting. OK. Let's just switch to a video. This is why we have videos. So let me just pause it a second. So I've just deployed the webhook. On this side, I've got the Azure Functions portal. Sorry, I've just deployed the webhook configuration, so the logic. Now I go to run this deployment, and I'm using that v1 image. So in this example, I'm doing a deployment, so the deployment actually succeeds, but as I'll hopefully show you, the pods won't be created. So we see it succeeded. And over here, we can see that our webhook ran. The text is a little bit small, but essentially it's run the validation. Hopefully we can see that a bit better now. If I now look at the pods for that deployment, what we'll see, or see events rather, we can see that event is pushed here. So we can see it said, failed to create, the webhook said, it's a bad image. If I do get pods, you can see there's no pods created. If I now run the v2 just to kind of prove that it's not blocking everything, we see the webhook ran again, but this time it didn't have an issue with the image because it was the v2 image, and now my pod is running. So hopefully that gives you a quick kind of feel for webhooks. Let's go back to the slides. Rushing through the demos a bit here. So webhooks give us a lot more control. What if we want even more control? If you're in the UK, we like taking back control, apparently. What if we want to build abstractions on top of the Kubernetes resources? So Kubernetes does this already. So if you look at a deployment in Kubernetes, that's an abstraction on top of replication controllers and pods. What if we want our own? What if we want to create entirely new resources within Kubernetes? What if we want to deploy a domain-specific object? We can do that. And what if we want to use kube control to manage those resources? We have a few options. First one is we can write an extension API server. This is actually quite a lot of work. You have to essentially implement an API server from scratch. You've got to set up your own persistence for the API server. It used to be the way people did this. Now you have the option of using custom resource definitions. It's probably the thing most people have heard of in this room, I suspect. And we have custom controllers. Now, custom resource definitions and custom controllers are linked together, but people often use just the term custom resource definitions in isolation. We'll dive into that a little bit in a second. So custom resource definitions, or CRDs as they're commonly called, is essentially a new resource type alongside the built-in ones. It allows us to create and delete these resources, and these things are stored within the etcd cluster, so we're not having to create our own persistence. The important thing to know is they're useless without a controller. Let's have a look anyway. So this is how we define a custom resource definition. So now the resource kind is custom resource definition. We have to give it an API group and a version, and then we have this scope. So the scope essentially is it either namespace scoped or cluster-wide scoped. And then we set up some metadata about it. So in my case, this thing's called a foo. It's got foos is the plural name, foo is the singular name. The resource kind is foo. And then I've even added a short name, FO. So like get PO for pods. What I can then do is I can create an instance of this resource. So now, much like I would create a deployment or a pod, I'm now creating a kind foo. And I can then put in pretty much wherever I want in that spec. So let's take a look at this. So I can, it's a little video, let's click that on. So what I can do is I can apply that custom resource definition. And once I have that, I can now start creating these resources. So now I can do kubectl applying a foo resource. I'm getting this, now I do get foo, and I'm get back that foo object. I can use the short name, it's great. And now I can delete it. And that's about all I can do. So yeah, great, I've just done CRUD essentially, and literally no logic. So you need these custom controllers. Now custom controllers, it's worth mentioning, they're not just for custom resources. You can actually customize the behavior of existing resources. So if those validating and mutating webhooks don't give you enough control, you can write a custom controller that can essentially do the things you want to do. They're often paired with custom resource definitions to essentially power those custom resources. They are typically implemented in Go. I don't think that's necessarily a hard requirement, but you do need to access the API server machinery, which is a client Go library. So I've only ever seen it implemented in Go. You may have heard the term operator. Broadly speaking, an operator is a custom resource definition along with its custom controller. Now, if you're thinking I'm going to go out and create my own custom, my own operators, there's actually a load of operators already out there. So a lot of the cloud providers have created operators to help integrate with their cloud. So AWS is probably a good example. They've created an AWS operator, which allows you to provision AWS resources as part of a Kubernetes deployment. So it's worth checking that list. If you want to create your own, it's not a trivial task, I should warn you. One option is to use this operator framework, which I think the CoreOS team released a little while back. The other option is there's an example custom controller within the Kubernetes documentation that you can kind of copy as well. There's also a workshop some people run. I think that's probably the best way. You really need some experience. It's not the easiest thing to do. So we're going to take a bit of a shift now. We've spent a fair bit of time talking about kind of scheduling and controlling and extending Kubernetes. I want to do a bit of a shift now and talk about scaling applications and clusters. So when we talk about autoscaling, we have a number of options. So horizontal pod autoscaler is the component which I'm sure most of you in this room are very familiar with. This thing allows us to essentially scale the number of pods we have in our deployment based on metrics. The original pod autoscaler used CPU and memory. The V2 is a lot more powerful. It allows us to use any metrics pretty much, and even external metrics. So we can scale a deployment based on the number of items in an Azure Service Bus queue, for example. Maybe not so well known is the vertical pod autoscaler. Now this is still in beta, but this allows us to increase the amount of resources allocated to a pod based on certain metrics. So the name kind of suggests the horizontal pod autoscaler is scaling out, the vertical pod autoscaler is scaling up. When we're scaling those pods, we can only scale to the limits of our current cluster size. So if we need to increase the size of a cluster, this is where the cluster autoscaler comes in. The cluster autoscaler essentially looks for pods which can't be scheduled and uses that as a metric to start increasing the size of the cluster. Now, in most cases, you're going to be running on a cloud, so this will interact with the cloud provider to start increasing the number of nodes. One of the challenges with the cluster autoscaler is the time it takes to scale the cluster. It might take 3, 4, 5, 10 minutes to increase the number of nodes in your cluster. What if your traffic is very spiky and you can't respond quick enough? This is where this project called the virtual kubelet, virtual node, comes in. How many people have heard of the virtual kubelet, virtual node? A couple of hands. Excellent. OK. The name is a little bit confusing, so hopefully I'll explain that as we go along. So this is an open source project. It was created by the Microsoft team. I think it's been donated now to the CNCF. Essentially allows you to connect an external compute resource into your Kubernetes cluster and interact with it as if it was a node within Kubernetes. I can see a few puzzled faces, so hopefully the next slide will explain it a little bit better. So what I've got in my cluster here, I've got 3 actual nodes, so whether they're bare metal or VMs. And then with the virtual kubelet, I create this virtual node. So when I look in the cluster, I see another node. But that's not actually a VM or a physical machine in my cluster. It's actually pointing to some external service which is powering it. This virtual kubelet exposes most of the functionality you'd expect to see within a pod and within the nodes. So as far as you're concerned, you're going to interact with it just like you would in Kubernetes, but the pods themselves are running somewhere else. So a number of implementations of this virtual kubelet. There's the Azure Container Instances one. So for those who don't know, Azure Container Instances is a lot of buzzwords here, is the serverless container offering from Azure. Allows you to run containers and pay per second for the containers while they're running. The similar service on AWS Fargate, so there's also a virtual kubelet implementation which sends containers to Fargate. And then similarly, we've got other implementations of Nomad, which is the HashiCorp's kind of container management platform, Service Fabric Mesh, Azure IoT Edge, and there's many others as well. So where is this, this kind of virtual node concept, where is it useful? So let's assume I've got my cluster, I've got 3 nodes in it, and I've got this virtual kubelet deployed. So I've created a virtual node. And I'm running, and my cluster's running hot. What I can do is I can start scaling my cluster up, but that's going to take some time. What do I do with the traffic in the meantime? Do I just drop it? What I can do is, through the virtual kubelet, I can actually push that workloads, that traffic, by deploying containers onto ACI. So I'm scaling my application up, and containers are being deployed onto ACI. So that's taking the load. I'm bursting into ACI, if you like. They're taking the load while I'm potentially scaling my cluster up. When that load dies away, those pods will come off that node. I stop paying for them. Within AKS, the virtual node is in preview. And you can just enable it with this one option down here. So let's have a look at a demo. And I think I'm going to use a video given the internet's not working. So I'll just pause this 1 second, so I'll set it up. So what I've done is I've deployed that virtual node. So I've enabled it in my cluster, my AKS cluster, and I've got, you can see here, I've got my 3 existing nodes, then that virtual kubelet has created this additional node. So this is what I mean. It looks like another node in Kubernetes. Yeah. I didn't need to pause it. If I take a closer look at that particular node, so if I do kubectl describe, you can see a load of stuff, but the bit that's relevant or interesting, so we've got some labels on there. We've got a label that says it's virtual kubelet. And then the key thing is we've got this taint. So we're tainting this. We're saying, don't schedule on this virtual kubelet unless you tolerate it. So when I said before about taints and tolerations, I don't want to be deploying containers to ACI. If I've got capacity within my existing cluster, I don't want to spend extra money. There's no point. So by tainting it, what I'm telling Kubernetes is don't use it unless you've been told to specifically use it. If I have a look at the deployments I've got on here, there's a few things running on this cluster. They're all related. But the bit that's interesting is this application called the online store. So that's that second one down. This is a web shop. I'll show you the UI in a second. And we can see everything is running on my actual nodes in my cluster. So nothing's running on the virtual node. Some machine is running on node 1, single instance. If I have a closer look at that deployment, that pod, what we'll see is it's got a toleration. It was right down the bottom. Let's scroll past it. Let's go back down. I should pretend I'm doing this for real, shouldn't I? Yeah, so you can see there. I'll just pause that a second because I'll show you the others as well. So you can see I've tolerated the no schedule. And incidentally, these are the additional tolerations I mentioned that Kubernetes adds sometimes. You can see not ready. So we're now tolerating that ACI. If I just added that, Kubernetes will start deploying onto that. Will start deploying onto there. But I don't want it to deploy on there unless it has to, unless there's no space in the existing cluster. So if we take a look at the, oops, let's just run that on a second. If we take a look at that deployment, I'll just pause it. We can see alongside that toleration, I've added an anti-affinity. So I've added a node affinity, but I've said where the type is not in virtual kubelet. So I'm telling it to prefer not to schedule on the virtual kubelet. So even though it tolerates the virtual kubelet, I'm telling it to prefer not to use the virtual kubelet. And this is how we get that flexibility where it won't use it unless it needs to. Perhaps there's a little bit kind of long-winded way of doing that. We'll see if we can maybe improve that in the future. So that's what it's doing. And there's that toleration I mentioned. So you can see we're tolerating it, but we're telling it not to. So this is the app itself. It's just a kind of web store selling various Microsoft products. And I can load up the cart. I think I've got like $13,000 worth in the cart or something. Yep. So what we're going to do is we're going to essentially hit this site with a load of with some load, and we're going to see how it behaves. So what I've got is I've got App Insights running on this, and we can see the request. There's literally 1 request per second coming in, and we can see our response time is very low. Now in the Cloud Shell, what I'll do is I'm going to start kicking off some load in that bottom corner. And what we can see up here is as soon as I kick that off, we should start seeing the request rate jump up. So we can see now it's jumped up massively. And also our request durations jumped up as well, because we're no longer responding quick enough. So we're taking now half a second. If I come over to the command window, we can have a look now at the pods. So what we can see now is we've got a lot more pods running. So the autoscaler is kicking in, and it's increasing the number of pods. We can see we've got some creating, some pending, and even one in an error. The interesting is where are these pods being created? So if we take a look with the, and incidentally, while I'm doing that, if you look over here, we can see now within a few seconds, our request duration has started to drop back down again. So we're now kind of handling that load. We've responded within a few seconds. We can see there's a lot more. The important thing is then it's wrapped around a little bit, but we can see most of these are running on the virtual node. So we didn't have enough capacity in our cluster. We've started scheduling onto virtual node, and we've spun up, tens of additional containers. I think this example scales up to about 60 containers. What we can do is if we then kill that load, this is where we do a bit of editing. I'm now going to kill that load test. So now the load's going to drop off. So we can see the requests have dropped off up here. And actually within about 90 seconds or so, the pods actually start coming off the ACI. So I edited the video here just so you're not waiting for 90 seconds. But we can see actually we're now back down to that single deployment, that single instance. We look at the pod autoscaler, we can see it's now down to 1 replica, and it was running 60. Just to kind of show you how quickly it responds again, in case you didn't catch it the first time, I'm going to run it again, or just the first bit, and hopefully we can see the time it takes to kick in and start scaling. So I've just kicked off the load, we can see the spike. I'm just repeating this, but hopefully now I've got a second chance to look at it. That first one, it hasn't started scaling. If I run it again, hasn't yet. So that's been about, 10 seconds? And there we are, we're starting to scale. So that's how quick it is. A lot quicker than trying to scale the cluster. So I'll just stop that there. So hopefully that gives you an idea of the virtual node, virtual kubelet concept. As I said, it's It's not a AKS-specific thing. You can run it in your own cluster if you want. Obviously, if you're going to run, so for example, you could set up a GKE cluster to burst into AKS, ACI if you wanted to, or Fargate. The only caution on that is you're going to have to give service credentials to the GKE deployment that has access to your AWS deployment. So that's the only thing to watch out for that. So we're going to take another shift now. How are we doing for time? Not too bad. So I'm going to finish on kind of service-to-service communications. Now, this is a section around service meshes, and I mentioned we'll go into a bit more detail in another session. So Kubernetes has a number of kind of options built in for doing service-to-service communications, but I think they're a little bit light. So we have the ability to kind of set pod security policies. We can have network security policies, so they allow us to kind of control what can talk to which other pods. We have an ingress. Now, anyone who's used the ingress knows that it's not too bad, but it's a little bit lacking in features. So with the ingress, what we can do is we can set up hostname and path-based routing, but we can't do anything else. We can't apply any kind of weighting to the traffic. We can essentially just send the traffic straight down to these services. If we had more control over the traffic, we can enable a number of additional scenarios. So we can do canary deployments. If we were able to send a certain amount of traffic to different pods, we can do canary deployments. Similarly, we could do A/B deployments. We can do one of my favorite things, which is launching darkly. So this is where we deploy a new instance of a service, and it receives a share, essentially a copy of the production traffic without actually being in production. So it allows you to launch a new version of a service, see how it manages with production traffic, and then decide whether you want to roll it out or not. And allows you to potentially route traffic between legacy and kind of cloud-native applications. As you're migrating an application, you're not going to suddenly, you need to potentially send traffic to a VM and then also send it to, to a Kubernetes cluster. And this is where some service meshes can potentially come in. So briefly, what is a service mesh? Essentially, it's infrastructure for handling service-to-service communications. So its job is essentially to ensure that you've got reliable delivery of messages through what we call a cloud-native modern application. The most well-known example of a service mesh is probably Istio, the most common project. It's an open source project being led by Google, Lyft, and IBM. And it runs on top of Kubernetes, although actually it does support other platforms as well. This is one of the things I love about Kubernetes is you can take Kubernetes and you can deploy something into Kubernetes which extends Kubernetes even more, makes it more powerful. So what does Istio give you? It allows you to do network kind of error handling. So this is not service, circuit breakers, retry logic, timeouts. And I'm sure most of you, if you're running your code, you're going to have libraries that do this. So .NET, we have Poly. Java has Finagle, I think. No, maybe not. I don't know any other platforms that well, clearly. But pushing these concerns down into the platform means that your code doesn't have to obviously have this implementation. And if you're using multiple different frameworks or platforms, you don't have to re-implement the logic. We can do rate limiting, similarly. We can do this traffic shifting and mirroring. So this is what I talked about. We can send 20% of the traffic to one deployment, maybe 80% to the other, and vary that number. Or mirroring is where we send a copy of the traffic to another service, and this is how we do that launching darkly. We can inject faults. So one of the nice things one of the challenges in microservices application is you need to be able to tolerate failure. And testing that can be a bit hard. So being able to consistently inject faults into a microservices architecture is really powerful, and Istio lets you do that. It lets you secure kind of service-to-service communications and also apply policies that say service A can only talk to service B and nothing else. And then because we're running kind of microservices, we can trace the requests as they go across the multiple underlying services. As I said, this is just touching on what Istio can do. Ben Hall is doing a talk immediately after this one, after the break, in room 4. We'll dive a little bit more. So let's just wrap up. So as hopefully you've seen, there's a lot of really powerful constructs within Kubernetes to kind of extend, control the behavior. As I said, you don't need to do this. As you find a requirement comes in, chances are there's a good capability built into the platform. Those webhooks are really quite powerful, and with minimal code, you can actually do quite a lot. And then the custom resources give you the ultimate extensibility, but you do have to work for it. Then that virtual node is potentially, in the future, we can have serverless Kubernetes clusters. We can have everything running in a virtual node, and we don't actually have to have any provisioned VMs at all. And if we're running in a managed Kubernetes provider, then we don't have master nodes either. We don't have anything, so it's pretty straightforward. So if you want to learn more, documentation for the Kubernetes documentation has all the things I talked about are in the Kubernetes documentation. They're perhaps not as easy to get your head around. That demo I did earlier with the scaling is on the Azure samples. I did a talk where I dive a little bit more into kind of service meshes and how they work with microservices in Sydney last year. And then if you want to learn more about any of these things I talked about, Katacoda is this awesome online learning platform. How many people have heard of Katacoda? Wow, so there's loads who haven't. Awesome. So Katacoda is this awesome online learning platform. So if you work with a corporate laptop and you can't install Docker and you can't install anything on your laptop, as long as you've got internet connection on a web browser, go to Katacoda and you can learn about all of the cloud-native technologies. So for example, there's a course on the operator framework, there's courses on Istio, there's courses on Kubernetes, Docker, GitHub, everything you can think of, Git, everything is on there. And speaking of Katacoda, as I mentioned a couple of times now, if you want to learn more about service meshes, and they are super cool, then Ben Hall, who's sitting at the back there, who created Katacoda, is doing a session in room 4, the next session. So I'd recommend going along to that. With that, I think we've got about 4 or 5 minutes for questions. Nope, no questions? Okay. In that case, thank you very much. We can go and get a coffee early.